Good morning, everybody. Welcome back to day 3 of the CubeSat Developers Workshop. As always, I want to start out the day by thanking all of our sponsors. They make this whole event possible. So, presenting sponsor this year is Millennium Space Systems. Our gold sponsors, DHV Technology, Blue Canyon Technologies. Silver sponsors, Maverick Space Systems. And our bronze sponsors are Leaf Space and Experior Laboratories. Can you give one more round of applause, please? All right. Not too many organizational notes this morning since it's the last day, but I do want to point out that an email was sent out to everybody who sort of registered or responded to the career fair that contains some organizational details about that event that starts at approximately 10:30, or basically when the presentations are done here. There should also be a verbal summary at 10:30 after the presentations are over, but if you signed up, make sure you check your email for the details. Want to remind you about that. Let's see, what else? Unfortunately, I have an unavoidable meeting for my day job that's going to keep me away until that 11:15, so I'm not going to be able to say goodbye to all of you, especially if you're heading out about 10:30. So if I don't get the chance to see you, I do want to thank you for coming. I really do enjoy seeing everybody, and I think it's been a fun event. If you're here for the career fair or here after that, hopefully I'll be able to see you, in person to say goodbye. So that's what's happening with me. We have our first presenter today. We have some presenters. Shaylin Miller and Alice Sikostovsky, I'm sorry about that, Alice, are going to be presenting on design and development of a CubeSat robotic arm for in-orbit inspection and servicing. So please welcome them.
Thank you. Hi, my name is Alice Sikostovsky.
Hi, and I'm Shaylin Miller.
And we're going to be presenting on the design and development of a CubeSat robotic arm for in-orbit inspection and servicing. And this is a research project we've been doing here at Cal Poly San Luis Obispo under the direction of Professor Dr. Stephen Kwok-Choon, along with 4 other team members who couldn't make it today. So just to give a brief overview, this research project has only been around for a couple of months. So we really only started this project in January, so please keep that in mind. This is kind of a first iteration. So our vision is to contribute to the sustainability and shared use of space. Our mission is to produce a cost-effective method for on-orbit maintenance, and our values for the mission are cost, usability, low complexity, and ease of deployment and operation.
And so for some of our mission statements, we wanted to design and develop a 4-degree of freedom CubeSat robotic arm. And we wanted it to have a series of revolute joints so that it could move and rotate to pick up objects or to service other satellites. And we want the robotic arm to function with both a camera and a LiDAR sensor. And for the first iteration, we decided that it will be controlled by us, but future iterations would hopefully be controlled via camera.
So here's our pretty high-level concept of operations. So first we would have deployment of the CubeSat, following detumble, orbital corrections, rendezvous with the satellite, robotic arm deployment, robotic arm maintenance, and then rendezvous back with the home satellite, and the CubeSat would repower at the home satellite.
For the actual concept of operation for the arm, we wanted to make sure that it deployed, it repositioned, then it did what it needed to do in the maintenance, then it would reposition again to then stow back inside of the CubeSat.
So our initial design for the robotic arm would feature 4 to 5 degrees of freedom with a revolute shoulder and elbow joint for in-plane transitional motion with the possibility of a 3rd joint for out-of-plane motion. And it'll feature 2 revolute wrist joints for roll and yaw motion of the end effector And we will have LiDAR and camera aided remote operation. So LiDAR to help with the coordination of the position of the object in the workspace, and the camera to help locate and grab the satellite or object once it's close enough.
Then moving on to our system architecture here, we have the CubeSat working with a Raspberry Pi to move the arm and the servo motors that are inside of the arm. And we have different connections for the power. We have the battery pack for it, as well as the transmitter/receiver, so that we can get data from the ground station and send data to the ground station as well.
So this is our high-level hardware layout. So there will be positional commands that will be sent wirelessly to the computer, and inverse kinematics determine the joint angular position. And then there's a single I2C bus that services all motor, actuation, and control units, and the Raspberry Pi and the LiDAR will continuously stream data to the controller. And then over there is our diagram of our high-level hardware. So the computer with the LiDAR, the Raspberry Pi, and the controller.
And we also are going to be having the computer finite state machine. It's got a diagram with how it's going to run through all of the code, and it's the computer waits for the data to be sent through the TCP socket, and with that, once the data is received, inverse kinematics will be done and run by the Raspberry Pi to ensure that the position of the arm is correct.
And here are all of our computer and LiDAR and optical sensors. So like I mentioned, we'll have a Raspberry Pi processing power and interfaces for sensors and actuators. So we'll have our Raspberry Pi, our Pi camera module, and our LiDAR rangefinder. And the LiDAR module is a lightweight and cheap LiDAR sensor with interface, and the Pi camera module is going to be used for video stream.
So here's our Mac layout. We are doing this so that we can have dual motor control for the robotic arm, and we want the control to be used to use an H bridge as well as an AntMega 32AP. We just figure that this is the best way for us to get the arm in position the way we want it to.
And this is our finite state machine. So the motor controller will wait until the address and sent data on the I2C bus, and the error is updated, and the state is going to be changed to moving, and the PID is used to change motor angular position until the error is going to be within a tolerance.
For the hardware of the motor, we have chosen a 268 RPM BDC motor, as well as a L239 and an AntMega 328P. The AntMega, it will be in an 8-bit AVR microcontroller, and the L239 will be used as the H bridge.
And then here's our controller layout. So we will have a microcontroller with IoT capabilities, so Wi-Fi and Bluetooth, and two two-way potentiometers monitor for changes. And when a change is detected, analog values will be changed to update the EF states, and new states are sent to the computer, and then the orientation will be updated as seen in the diagram on the right.
For the controller state machine, the controller will update the end effector position using input from 2 joysticks. We're going to be moving it remotely, so each joystick is a 2-way potentiometer, allowing for 4 degrees of freedom control.
And then here is our controller hardware, so the ESP32-C3 and the joystick that we just mentioned, which is a 2-axis joystick. The ESP32 will provide a way to wirelessly wirelessly connect to the Raspberry Pi, and the analog joystick on the right will provide a user interface, and so we'll be remotely controlling it. And here's our end effector design, which is going to be a 3-prong clamp end effector right there. And each prong will feature a comfortable surface for increased traction. A Raspberry Pi system will be used for control and actuation of the arm end effector, and gecko tape will be used for the building of the end effector, and gecko tape is a non-chemical adhesive tape, so we thought this would be best for the robotic arm. And for the actual CAD layout, here is our design. So we will have the basic frame of a 3U CubeSat right there, and with 3 servos, 2 arms, and a 3-prong end effector with 3 joints as shown previously. And then here is the exploded view right here. And then this slide shows our stowed arm configuration, so how the arm will be stowed in the CubeSat bus during deployment. And that's the extended arm configuration. So this is how the arm will look and function when it is completing tasks. Thank you. Yeah, I think so. Any questions? Yes. Oh, 1 second. What? I think we do have it somewhere here. Yeah, it's a Raspberry Pi 4B. I couldn't remember off the top of my head because there are so many. Yes. Yes. Yes.
Good morning. I'm dead impressed by how ambitious this is. As many of us must be, I mean, the number of independent modules you've got going here. Just dead impressed. Just a very simple question. The LiDAR and the Pi camera module, you've used these in vacuum before?
So no, we just started this project in January, so this first iteration will just be testing on the ground.
Okay. And so you may swap those parts out later on?
Yes, it's a possibility. So we haven't done any sort of vacuum or thermal or TVAC testing yet.
There might be literature, open literature that.
Oh yes, there is literature, but well, I was just saying our team hasn't done it. Yeah. Where? Oh yes. Sorry, could you repeat the question, please? Oh.
So we chose the Raspberry Pi just for the simplicity of it. Our software lead likes Raspberry Pi and has used it before, so we have decided to do something that we were comfortable with for the first iteration.
Yeah, it seemed like the simplest method for the first iteration. Yes. Yeah, that is definitely something we're going to look into. We have examined previous literature that used motors in vacuum, but this is something we're going to be testing once we once we do our on-the-ground testing. Yes.
I think our software lead is using C++.
Yeah, I believe we have a software team lead and he's not here, but yeah, I think C++. Yeah. Yes. Yeah, so it will be deployed out of the home satellite right now. Right now, our vision is to deploy out of the home satellite, and then the robotic arm will deploy from the CubeSat. Obviously, it'll still be attached to the CubeSat, but then it'll perform on-orbit maintenance and servicing. That's our vision right now, but for this project in general, we've mostly been focused on the initial design of the robotic arm itself and the CAD, and how it's going to interface with everything, because we've only been doing this project since January, so that really hasn't been the focus of our project quite yet, but that is our vision. Thank you so much.
Thank you, Alice and Shaylin. Next up, please help me in welcoming Adam El-Sharhawi with Bronco Space and Cal Poly Pomona, presenting a low-cost mobile ground station kit for amateur UHF communications.
Good morning, everyone. Thanks for coming. Today, I'm Adam El-Sharhawi, and I'm here from Bronco Space at Cal Poly Pomona, the other Cal Poly. I'm here to talk about our low-cost ground station architecture that we use with all of our CubeSat launch, our past CubeSat projects. So the main objective of this low-cost ground station was actually founded out of necessity, because on our second CubeSat launch on Transporter 6, we had issues with getting because we currently have a Uniclogs ground station setup, but we did not have it built at that time, and we wanted a way to get AOS after launch without having to use a third-party ground station. So we built this setup a little bit more crudely than it is put together today. But it was a very big learning opportunity for me and other people around the lab to be able to set up a ground station from scratch at such a low cost and at a very accessible skill level. So as a student group, getting anything permanent on campus is very complicated. I'm sure many of you know. And even though we've been around for around almost 5 years, we've put about 4 satellites into space, we still haven't had anybody come on to our lab to even look at our case to put our ground station on the roof. So it is actually currently parked in a parking spot, which it has been a back and forth about whether or not it's okay to be there, but we've been deciding on if we should put a parking passer on it or not. So far, no tickets, so it's been good so far. But as you can see, this ground station is a pretty big guy. It's not really easy to move around. It's not really something that's super accessible to just like start working on. It's kind of daunting, especially as like a student who has no prior experience working on ground stations. You can also see here when we first built it, just to move it from our lab where we assembled it to the parking spot, we had to throw it on the truck and roll it over. So it's not a really mobile unit, which I think is one of the strengths of our low-cost architecture. So the low-cost architecture is nothing fancy. It's by no stretch of the imagination any like new advancement in RF technology. However, it is something that I think is very important and integral to the educational aspect of using CubeSats. So the main structure is a Celestron telescope mount that we grabbed from one of the existing telescopes we own, but you could probably find one for pretty cheap. It's a 10-element handheld Yagi, a SDR, and then there's some telescope tracking software that I used to do the passes. So the setup is pretty simple. Honestly, it's kind of humorous how simple. I go out there with like my Star Tracker app on my phone, because I usually do this during the day, and I line it up on the end of the Yagi, and I do my 2-point align or 2-star align on the Celestron, and so far that has worked very well. This is obviously low cost, so it's not like a very complex system, but it is something that I think is very important for students to have a understanding. Especially, I think everybody has had the experience where you're spending hours of sweat and tears trying to get something to work, and when you finally have that moment of like a received packet, especially in this case, I think it's more transformative than just buying an off-the-shelf unit and it working right away. It really builds character, and it builds a sense of understanding that's pretty different from just buying something out of the box. This is the software that I'm using. It is not obviously like as good as if I had used maybe a custom software, but it works pretty well, and I think that is the main point of this whole architecture, is that it's not obviously like a groundbreaking technology, but it is something that I'm an aerospace engineering student. I'm not an electrical engineering student. I don't know like too much about RF in terms of like the intricacies, but I put together a ground station. I've done multiple passes with our satellites and other satellites, and I think that speaks to the architecture itself, and I think that speaks to what I believe CubeSats are really good at, is letting people who are not necessarily the most people who are not necessarily involved in the intricacies of the design of each part of the satellite, to be able to have an understanding for the encompassing like life cycle. So yeah. So I think I touched on this already, but as an educational tool, I think that having something that is not, I don't know. So on the Uniclogs one that we have, it is obviously not a cheap ground station. Like, you can make the argument, why even go for a custom-made ground station when you can buy something that works? And I think that for a lot of student groups, not just having something permanent, but having funding is always a complicated endeavor. And I think having a ground station that is sub $1,000 is pretty accessible for most student groups. And even you can extend that to other amateur groups, like even with like a high school. We've had a few high schools make satellites. And I think that as a tool for education, it is very important to be able to see from start to finish the life cycle of a CubeSat launch or CubeSat mission. So you can have a hand in the assembly, you can have a hand in the ground station and con ops or mission ops. And I think that provides a lot in terms of education. Yeah, I think that obviously, like as I said, I'm not an RF engineer. I'm an aerospace engineering student, and I think that this architecture, being simple as it is, it has provided me a lot of knowledge of the overall life cycle of a CubeSat mission. I think that it is something that is really worthwhile and is worth investing into as a student organization, because you're able to do your own mission ops. You're able to have your hands on and get your hands dirty with the like with your passes and getting data down. And I think that's something that's really important and very very important for student groups in general. But yeah, it's a very short presentation, but I can open up questions, I guess. Yeah. I haven't tried it. I haven't tried it yet on the we call it Pointy Boy. We haven't tried it yet on Pointy. However, that is something I've wanted to go into in the future. I think another upgrade that would be very interesting. I don't know if anybody has saw that. I think there was a talk at SmallSat last year about using a bigger celestron telescope for optical comms. I think that'd be something that'd be cool. But yeah, uplink would be very, very cool. It's just, I think I'd have to spend a lot more time on it, but yeah, it would be interesting.
Have you considered an extension to this to S-band?
No, I haven't, but that would be interesting. Because the reason why we've used the UHF is usually we go through our amateur bands for our comps, but I think S-band would be an interesting upgrade. I feel like there's a lot of branches you could take this, which is what I like about it, since it is just a antenna attached to a telescope mount. So there's a lot of things you can do with it. But S-band would be interesting. Yeah. Thank you.
Thank you so much, Adam. Next up, please help me in welcoming Marissa Duplessis with CubeSpace Satellite Systems, presenting an ongoing investigation on the measurement, analysis, and simulation of microvibrations with the aim to characterize reaction wheels for high-performance imaging missions.
Hi, can you guys hear me? Thank you so much. So, good morning. My name is Marissa Duplessis, and I am part of the CubeSpace ADCS AIT team. Today, I'm going to be presenting my ongoing master's thesis. Shorten the title a bit because everyone stumbles over their words if they say it. But what I'm talking about is the characterization of reaction wheels, especially when they're used for high-performance imaging missions. So before I start, I'd just like to tell you a bit about what CubeSpace does as a company. We are a company that designs and manufactures ADCS systems. The company started as a spin-out from Stellenbosch University in 2014. We're currently controlling over 350 satellites in orbit, and we've supplied ADCS components to we've supplied over 3,000 ADCS components to clients worldwide. We initially started with only CubeSats, but we have recently scaled to microsats, and during 2024, we're going to be opening offices in the EU and the US. The research I am conducting is focused on CubeSpace reaction wheels, and it will serve as both a design and quality tool once complete. All right, so as I mentioned, the focus of my thesis is to characterize reaction wheels when they're utilized for high-performance imaging missions. The missions like these, with high ground resolution specifications, demand an exceptionally stable platform. The platform instabilities during imaging operations can result in several undesired effects, such as shown in the images here, image smear, image blur, resolution degradation, and of course a lot of problems in post-processing and analysis. The stability of a satellite is highly influenced by the microvibrations emanating from its subsystems. Microvibrations are typically low-level disturbances produced by moving subsystems such as the reaction wheels. So that's how the reaction wheel and the stability of the imager and the satellite relate to each other. The characterization and analysis of microvibrations emanated by reaction wheels have thus become quite a relevant topic in the attitude control community, especially as imaging technology just keeps on getting better as time goes on. The objectives of this master's thesis is to classify various origins of microvibrations in conventional reaction wheels and to develop a theoretical model for the reaction wheel to predict those microvibrations. This was done through a series of mathematical derivations as well as various sets of experiments. Ultimately, the goal is to predict the forces and the torques emanating from reaction wheels during standard operation, as well as to mitigate the microvibrations caused by them. All right, so an important contextual part of the research conducted so far was to define microvibrations, as well as classify the sources from which they emanate in conventional reaction wheels. Microvibrations are periodic microdisturbances that manifest as 3 forces and 3 torques in the x, y, and z axes, respectively. These are generated during the standard operation of reaction wheels. They're typically low amplitude mechanical vibrations or disturbances, and they occur in low frequency range, spanning from 1 Hz up to 1 kHz. Various sources actually just classify the upper limit of a microvibration frequency at 500 Hz, and that is also what I used with most of my analysis in experiments. A common way to represent these microvibrations is using a waterfall plot, as you can see in the slide there. A waterfall plot is a way of presenting the amplitude of these microvibrations as a function of the rotational wheel speed in the frequency domain. These microvibrations in reaction wheels can present as signals with various types of characteristics. The first of these signals being the structural cage modes or the resonance points of the modes. The resonance points are not linearly dependent on the wheel speed, and you are very into this. I'm loving it. Thank you so much. Every time I look up, he's sitting there going, yes, that's right, that's true. So the structural cage modes are not linearly dependent on the rotational speed, and they can easily be identified in the waterfall plot, as you can see there with the red line. Another type of signal that we can easily identify is engine orders, or what I refer to as engine orders. Just give me a second, sorry. Also the first time I've been working with a microphone like this. So one of the issues of having curly hair is it's absolutely everywhere. All right, so the engine orders, contrary to the natural frequencies, they are dependent on the rotational frequency or rotational speed of the wheel. Both of these signals, representing essentially a combination of microvibrations in the reaction wheel, can be easily identified and visualized in a waterfall plot. That's why we use that when we represent the characteristics of the wheel. All right, so just a bit more detail about the structural cage modes. They're also referred to as natural frequencies or the eigenmodes of the system. The natural frequencies of a reaction wheel present as the first 6 modes of the mechanical system. We expect 3 translational modes as well as 3 rotational modes. Because the wheel is spinning freely around its spin axis, we actually ignore the z-axis when we look at these modes, which leaves us with 5 degrees of freedom and the 5 modes shown here. The rocking wheel mode is the one that you can see as a V. Actually, I've got this. The rocking wheel mode is the one that you can see presenting as a V there, and that is classified as both forward and backwards whirl. An example of all the structural cage modes can also be seen here in blue on the waterfall plot. So it's quite easy to see that all of the structural cage modes are not dependent on the wheel speed. They are inherent to the reaction wheel and the geometry of the reaction wheel. Then the first engine order that we'll be looking at is unbalance. Unbalance is often the most significant source of microvibration emanated by a reaction wheel, and it's caused by a residual uneven distribution of mass in the flywheel around the axis of rotation. Unbalance can be classified as both static or dynamic unbalance, represented by the ms over there for static and the md over here for dynamic. Both of these masses respectively cause forces and torques around the rotor's axis of rotation. In practice, both static and dynamic unbalance present as one single parameter called or what I refer to as the dynamic uncoupled, dynamic coupled unbalance. Right, so another engine order is ball bearing imperfections. This is the one that's giving me sleepless nights because it seems like it's basically impossible to model, but I will talk about it just because I need to mention it. These ball bearing imperfections can cause peaks at the outer and the inner race ball pass frequency, the fundamental cage frequency, also relative to the outer and the inner race, as well as the ball spin frequency. The equations presented in this table can then be used to predict the peaks at where we expect these fundamental frequencies to be causing disturbances during operation of the wheel. The last engine order is torque ripple. So what that is a variation in the torque output of a motor as it rotates through a complete revolution. Torque ripple is primarily caused by the interaction between the magnetic fields of the rotor and the stator. The four main types of torque ripple is presented in the slide here, with commutation torque, zero cross-section, harmonic torque ripple, and the most important one, or the most relevant one to me, cogging torque. Cogging torque is caused by forces generated between the permanent magnets in the rotor and the teeth of the stator. The fundamental frequency of cogging torque is the function of the number of magnetic pole pairs in the motor and the rotational speed. So the equation presented here can then also be used to predict the frequencies where we expect disturbances caused by cogging torque when we're doing our FFT analysis. All right, so getting to the fun stuff, the theoretical model. So with knowledge about the microvibration sources in conventional reaction wheels, the next step for me in my research was to start creating a theoretical model using the reaction wheel geometry as well as predefined Euler angle rotations. So it took me a while to conceptualize, but I'm going to try and explain it in one or two sentences. The Euler angles were used to define the rigid body rotations of the flywheel, and it's also used to translate one fixed coordinate frame to another. So when you have that type of rotation, as soon as the flywheel starts to rotate, it sort of creates a new frame of reference for itself. Once that frame of reference is there and it's rotating, it's creating a next one. So the rotation chosen for me during my calculations was XYZ, or sometimes also referred to as 213. All right, so the model that I will be presenting does not currently take the ball bearing imperfections into account or the torque ripple. The model is simply a geometric model of the reaction wheel, and it is used to predict the natural frequencies or the structural cage modes, as well as the unbalance of the wheel. As a first step, the equation of motion for the diagram shown there was calculated using the Lagrange equation. For that, I needed to determine the kinetic energy in the system, T, as well as the potential energy stored in the springs. What I did not mention is that I am modeling both the two bearings as a spring dashpot system, and the flywheel is simply a rigid disc rotating on a rigid shaft. So breaking it down like this, it seems to make it make a lot more sense than it actually felt like initially. All right, so I determined the, the kinetic energy of the system T, as well as the potential energy stored in the springs K. After that was done, I took into account the external forces generated by the viscous bearings and defined that as delta, the viscous dampers, defined that as delta W. So for each degree of freedom in the system, of which there is 5, an equation of motion was determined using the Euler-Lagrange equation here. I'm not going into that because it took me quite a while to understand it myself, and I don't think I can explain it yet. So the example equation here is for the translational degree of freedom x, and as I said, that was done for each degree of freedom. Right, the set of equations, the set of the 5 equations presented in the previous slide, represent essentially a theoretical model of a balanced rotor bearing system. It was linearized and rearranged into matrix form to become the equation you see there. As you can see, it's quite a simple second-order differential equation, if you look at it like that, where a, v, and u are your acceleration, speed, and translational vectors, respectively, where each of these vectors represent all 5 degrees of freedom of the system. Now, of course, in practice, every reaction wheel has some form of unbalance. These unbalanced masses were added as I mentioned, the coupled dynamic unbalance. So the unbalanced masses were added together as MD and MS, respectively, for the static unbalance and the dynamic unbalance. The impact of this on the calculations is essentially just that the total mass now increases from only the mass of the balanced flywheel to include the static mass as well as the dynamic unbalanced mass. This causes the translational motion to now take into account the total mass as well as the external excitation caused by US, the static unbalance. In the rocking motions, we now need to consider the added inertia or the additional inertia, as well as the excitation of the dynamic unbalance UD. So the same method as for the balanced wheel was then followed, and through approximation of the inertia terms and further rearrangement, the equations of motion for the unbalanced wheel can then be outputted as presented in the slide over here. I was told that you should not put math on a slide, but seeing as I put so much time into it, I thought I would just show you guys that it really does exist. All right, so now here the part that actually makes sense. The set of equations I showed in the previous slide are then considered the basic form of the theoretical microvibration model, and they can be presented in matrix form as a second-order differential equation here. So important thing to note is that my C term as well as my unbalanced term is speed and time dependent. Still, A, V, and U are my state vectors representing acceleration, speed, and translation. Right, so it's very nice to have this, but what do we actually do with it? So currently, the model that I have done yields 2 outputs. The first of that output being the Campbell diagram shown here. All right, the Campbell diagram is a graphical representation of the natural frequencies or the eigenfrequencies of a rotating structure presented as a function of the rotating speed. It is an essential tool for understanding vibration analysis and characteristics of the reaction wheel. The Campbell diagram was generated by, sorry, this microphone is insane. The Campbell diagram was generated by neglecting the system damping as well as the external excitation caused by the dynamic and the static unbalance. The state matrix A was then determined for the entire system, and the eigenvalues of A was calculated at each set speed and plotted on the graph over here. So what we now have is a nice top view of the radial translation mode, the structural cage modes that I referenced earlier, the axial translation mode, as well as the forward and backwards rocking wheel modes. So for this particular wheel, it's clear to see that the structural cage modes will not interact with the unbalanced peaks that you can see here, and that's a very good thing, because what we can now avoid is interaction between these types of disturbances and unwanted superposition and unwanted amplification of modes. All right, so the second output of the model is a FFT response at set speeds. So as this is a simple, I should stop saying simple, as this is a second-order differential equation, it is quite nice to perform a fast Fourier transform analysis on them. So this was done by analyzing the system at set speeds. It's achieved by translating the mathematical model I showed in the previous slide to a Simulink block model that I've shown you here. At each wheel speed, the system can then be solved through Simulink, and the acceleration vector A is then determined. For each degree of freedom, A is multiplied by either the mass or the inertia, giving us the forces and the torques as a function of time, respectively. These signals can then be transformed into the frequency domain, and the FFT plots for each set speed can be stacked to create a waterfall diagram that's comparable to the experimental data. So these are the two things that I've, at this stage, gotten out of the model that I've done. All right, so the next step after having the model was to actually do some experiments to gather some data on microvibrations in reaction wheels. The experimental setup that was used to measure these microvibrations emanating from the wheel consisted of a piezoelectric force torque sensor, multiple lab charge amps, pneumatic isolating system, and processing software JBeam, all acquired from Kistler. The sensors are placed onto passive vibration isolators, which you can see here. Oh, sorry. There we go. Passive vibration isolators that you can see there. They are mounted onto a rigid structure, and that structure supports a 250 kilogram granite plate. This is done so that when the measurements are taken, we can ensure that they're taken with a relative to a stable low vibrational base over there. So when I am, for instance, walking past while I'm doing my measurements, the microvibrations caused by me walking gets attenuated through the entire system and hopefully does not propagate through to the sensor. So the tests conducted were done by setting set speed commands at set timestamps to the wheel. Let me just go. Okay. So the forces and the torques that were then generated by the wheel were collected through the Kistler sensor and through the J-beam software as a function of time. Once again, we could perform the FFT on each degree of freedom for the system, and that FFT was then split into a matrix to be presented as a waterfall plot that you can see in the slide here. So through the software, you get to simply get your forces on this side and your torques as a function of time, perform FFT on that, split it into a matrix that is defined by your time steps, and you get an entire overview, bird's eye view of the microvibration characteristics of a reaction wheel. What I'm showing you here is a FFT that I performed on one of the wheels that I measured. This is the X force at 6,000 RPM, which is the maximum speed for the specific wheel that I was testing. In red, the equations that I showed very much in the beginning using, or to predict the ball bearing fundamental frequencies, they were used to predict where we could expect some disturbances to appear. And as you can see, I'm pretty happy with the results. It seems like it cannot be coincidental. It's pretty much, pretty much spot on. The black lines over there is then also the unbalance that I just as a sort of sanity check also added to make sure that I am where I think I am. All right, so this is the data that I currently have, and obviously we're just going to continue doing more and more tests, getting more and more done. Right, so the work that I completed up to this point was to characterize microvibration sources in conventional reaction wheels. We developed a basic theoretical model of the reaction wheel to try and predict these microvibrations, and we designed and implemented an experimental setup to measure the microvibrations in reaction wheels. The thesis is still ongoing, and it's only planned to end in 2025. So the developed theoretical model will be refined through further experiments and further analysis of the parameters as well. The ball bearing imperfections and the torque ripples will be added to the model so that we can have a full view of the characteristics of the reaction wheel. Finally, which is an important part, how we relate back to the satellite stability mentioned in the title in the first few slides, is that the propagation of the microvibrations emanating from the reaction wheel through the entire system will be investigated through further experiments that we will perform on the Kistler sensor, as well as an air-bearing setup that's currently in progress. The final goal will be to successfully predict and then mitigate microvibrations occurring at undesired frequencies and amplitudes. So hopefully I'll see you all next year with further experimental results and a complete validated model to show for it. Thank you so much. All right, I'm guessing I need to ask if anyone has any questions. Sure, okay, yes, you there in the middle. Sorry, you said damping? Yeah, damping. Is difficult to model? Yeah, do you have any specific model that you follow to use that in your model? Yes, so through research and without revealing too much, there's quite a lot of papers that actually do go into this. But I was chatting to my mechanical team, and they were laughing at me because if you look at this Campbell diagram, what I did right there. So sometimes I think the best way to model it is to assume it's zero. But yes, I do take that into account, and especially with the frequency response over here, you can't just set it to zero, but through research, we've gotten some form of approximation. And the thing with bearings, unfortunately, is that each one is different. We've taken a few bearings apart and put them under microscopes, tried to figure it out, tried to define the parameters, but it is still a work in progress, and I have a year and a half or so to nicely solidify that. But yes, that is one of the main issues that I am focusing on currently, or the most difficult things to model. If that, well, I don't know if that answers your question, but it gives you gives you some context. Yes, there were some questions here.
I think you said the ball bearing model specifically was like impossible to model. Can you speak a little bit more to that?
Well, I mean, from answering what he said, so often first of all, the motors that we're using, I don't have the specific parameters of the bearings, so I needed to, like I say, take them apart, I needed to investigate them and physically measure them to sort of get my parameters. The stiffness of the ball bearing, so the spring stiffness, is a parameter that you often get in a data sheet of a bearing, but the damping coefficient is unfortunately something that is not as straightforward. So there's a lot of math involved, and there's a lot of let's hope, and normally this is the case, but that's why essentially I've got an issue. And the thing with any moving subsystem, especially bearings, is that today it looks like this. I'm using a next one, and it has a slightly different form factor, or it's been handled a bit differently than this one, and now I'm getting different results. So bearings are very inconsistent to model, so we're trying to approximate them and get them to a point where we can say, okay, this is sort of what would happen most of the time. Yeah. You also had a question.
Yeah, so say once you learn how to predict and when these microvibrations will happen, do you have any methods or like your thought methods how you actually can prevent that?
Yes, so interestingly enough, there is a reason why I did not put that on the slide. Interestingly, the most easy way to do that is using dampers. So what we have is at CubeSpace a few clients who've actually requested that. We are currently in, the nice thing about doing your master's and working for the company is you sort of blur the lines there. But what we're doing is we're experimenting with different rubber dampers, playing with the stiffness, because what we have seen is, it's actually quite an interesting image, we can chat afterwards, but what we have seen is these dampers do mitigate microvibrations, so they completely erase them to a certain point, but as with any system, they also have a natural frequency. So what we do need to be careful of is that natural frequency being too low and then interacting with the unbalanced harmonics of the wheel and actually causing unwanted peaks at different frequencies. So it's very much for us at this stage, an experimental back and forth to try and figure out what is the perfect way to do this. But we've gotten there. It was just more than one iteration of trying. Yeah. Anyone else? Yes, hi sir. Mm-hmm. So can I model the center of mass of the flywheel?
Yes, so because practically it is very difficult to find real center of mass. So it's always there some errors.
Yes, so where I am lucky is because I am focusing my research specifically on CubeSpace, is I have access to all the design files and all of the dimensions and tolerances. So like you said, there will always be some error, but the point at which we have a flywheel that has a slightly different form factor than the simplified disk that I showed on the image. It is sort of an overhanging type thing, but through having access to the lowest level of those CADs, I could sort of translate them into something that's digestible and something that we could hopefully as accurately as possible in fact do simulate or model the center of mass accurately enough. But I mean, with mechanical systems, obviously I've been chatting to our mechanical engineers quite often, and one of these things, the words that they love to use is approximation. So we're trying our very best, but I think that's what makes the equipment. So the Kistler sensor and the air bearing is both in-house equipment that we have. So I could whatever I think could work, I have access to all of those equipment, so I could just go down, do my tests, and see if I was remotely close to it or not. I hope that answers your question. Yes?
Hi, I'm just curious if you've done any validation to ensure that your Kistler setup is isolated from external disturbances?
Yes, so what we've done is we've obviously set up the entire thing. We've done a lot of research, and actually through previous people who've used that sensor, and we've had sessions with Kistler themselves and what they've recommended for us. What we've then done afterwards is with known masses and known forces, we've used equipment that's, to the less than a millimeter accurate, and applied known forces to the sensor, seen how it reacts. So yeah, we haven't gotten anyone to come calibrate it as of yet, because it's only about 6 months old, but very much accurate from what we've sort of derived our own set of experiments to determine that, and we're quite happy with the results. Yeah, very, very efficient sensor. If you speak next to it, you'll see some peaks. It's insane. Yeah. All right, is that it? Cool. Thank you so much for your time. I really appreciate it.
Thank you so much, Marissa. Next, please help me in welcoming Dr. Jose Velasco with Chasqui, presenting Cislunar omnidirectional optical terminal for small sats.
Morning, my name is Jose Velasco. I am with Chasqui Inc. Chasqui is a small company that is member of the Caltech Innovation Center. So we're located in Pasadena, California. And today I'm very excited to talk to you about our omnidirectional optical terminal that we are developing for small sats. Specifically, we are developing this terminal for Cislunar applications. Before I continue, I would like to acknowledge our sponsors. This work I'm presenting today has been funded by the NASA under the small business contract by NASA and in part by the National Science Foundation, also under a small business innovation research contract. The outline of the presentation, I'm going to talk, I'll give an introduction of what's Chasqui all about. I'll talk about the network we're implementing that we call INSPIRE. Then I'll focus on the omnidirectional optical terminal that we call the OOT, omnidirectional optical terminal, that is an enabler of INSPIRE. I'll talk about the status of the OOT, and I'll finalize with a couple of conclusions. So what is Chasqui all about? Really, what we want to do is to provide the space internet. So we want to be a provider of the space internet. So that's a big goal. So how do we do that? So we want to implement what we call INSPIRE. So INSPIRE is the Interplanetary Space Internet. It's a network. It's a network of swarms. So each node in that network is composed of a swarm of small sats. And those small sats are optically enabled. So they use lasers for connectivity. And we call those small sats spherosats. So let me show you an image of INSPIRE. So INSPIRE is, as I said, it's a network that we want to deploy along the solar system, including the inner solar system, the outer solar system, and cislunar space. And the network, as I indicated before, it will consist of swarms. Each node in a network could be a swarm. So the way you see it, the architecture you see here has been patented, actually. And we have received a patent from the US Patent Office a couple of weeks ago. So how will you do this? How will you use these networks? Let's say you have a mission in Enceladus, a deep space mission. And you want to bring data back from Enceladus all the way to Earth. So we use those nodes, relay nodes, and bring the data all the way back to Earth. Again, we use swarms as the nodes for this network. If we look at the Cislunar network, which is the one we're tackling first, then you will see this. So you see the nodes. We have a GeoInspire. We have 8 nodes, 8 swarms. We have the L1 Inspire. We have 4 swarms. And then L2 Inspire. We have also 4 swarms. A total of 16 swarms, and each swarm, as I said before, is composed of optically enabled small sat. We are also looking at ground stations. We're actively working to not only use but deploy ground stations, optical enabled ground stations. They might have some RF backup, but it will be mostly optical. So if you look at the node, as I say, it's a swarm. Oh, one more thing. We plan to enable all the swarms, all the CubeSats in this network with DTN, Delayed Torrent Network. So DTN, for the ones who don't know much about it, is a network very similar to the internet. So DTN is similar to TCP/IP, and what it has, in addition to the typical layers that you see on the upper left, it has a bundle layer that allows you for delays. Any delay, especially in space where you can break line of sight, it counts for that. In addition, the bundle layer at the packet level, it has a field where you can actually encrypt it. You can highly encrypt it, the signal. So you can create a very secure network, not only in Cislunar space, but beyond. So that we are very excited about that opportunity, being able to use DTN. So let's look at the swarm. So this is a typical swarm. This is the swarm we want to use for Cislunar space. If you go beyond that, the amount of spacecraft will be larger, obviously, because the distances will be larger. If we want to close the link, we need more spacecraft. But let's take a look at this one. So what you have is a leader in the middle, and then you have, in this case, 4 followers. So under our design, what we like to do is the leader will transmit beams to the followers. You see in red. You can see there are 2 beams superimposed. The red is the transmitting beams from the leader, and the orange beams are coming from the followers. So by having constantly, you have these beams on. So what that allows you to do is that the 5 spacecraft are connected, almost like a fiber, continuously connected. And with that, you can synchronize events, you can synchronize clocks. For instance, if the satellites carry a radar system in addition to the communications, so you can synchronize the transmission of the radar to be simultaneous. Or going back to communications, in our case, we have these large optical terminals. What we can do is we can synchronize the transmission of the 5 terminals so that the transmitted power, in this case, will be 5 times. On receive, you can do the same. You can synchronize the reception of the signals, and then you can power combine the signals and improve your SNR. So also, you could have multiple different instruments on each spacecraft. So you can do data fusion, all because you are connected via this optical terminal. So that's the terminal which is the focus of this presentation, the omnidirectional optical terminal. And before I go to that, this is the CubeSat. That is the Lego of our network. So we're building the network based on this CubeSat. So what is new about this CubeSat is that it has 2 optical terminals. It has the omnidirectional optical terminal that we're discussing today. It has a new terminal that we are developing that we call the long-range optical terminal. So that terminal has large apertures. It's a gimbal system. We have 2, 4, or 6 apertures. And those apertures are designed for high data rate. So in combination with that, having the OOT and the LRAT, then we can achieve very high data rate connectivity in Cislunar space and beyond. Another thing, having the OOT in place, it makes this spacecraft swarm ready. By having the idea that any spacecraft that have the OOT installed in it, it could become part of a swarm seamlessly. So that is the benefit of CubeSat. So now it has other components, proven components that we plan to install in the spacecraft. So this is being funded currently by the National Science Foundation. So we plan to build this next year. So these are some of the technologies that we have identified that are important for the INSPIRE realizing. So today we'll talk about the interspace optical communicator, which is the OOT. Here's a picture of it. So for some of you that haven't seen it, has an array of transceivers, has 6 transceivers, has AOA detectors, has 20 detectors. So in principle, this device could allow to have 6 simultaneous links. And so what are the goals for this design? We want to have three basic goals that kind of dictate the architectural design of this terminal. First, we want to get gigabit level communications, full sky coverage, and then be able to do multiple simultaneous links. So we've been working on this for the past, initially I worked on this at JPL, NASA JPL, and then I left JPL a couple of years ago, and now we are developing this at Chasqui. So the past year and a half, we've been working on designing this OOT. So these are the parameters, the main parameters that we are pursuing. You can see we are looking at distances of about 2,000 kilometers. Wavelength is about 1550 nanometers. Each optical aperture transmitting 1 watt. And in this case, right now, we're using a 15 millimeter aperture, which is the fast steering mirror. So all combined, then we also have run simulations with a link budget simulator provided we obtained from NASA. It's called SOSLAT. And so here you can see, on the vertical, you can see that's the link margin versus distance. This is for 1 gigabit per second. So you can see you could get about 2,000 kilometers for those parameters. Similar to, these are the parameters I discussed before. Now I would say, what about other data rates? So you can, here we show multiple rates. You can see we can go from 10 megabits per second to 10 gigabits per second, 100 megabits per second to 10 gigabits per second. So you can see being 1,000 kilometers, in principle, you could get, you can achieve a rate of 10 gigabits per second. And the other end, you could do maybe a few thousand kilometers at 100 megabits per second. Again, details of this link budget, if you want to look at that, we just published a paper. And if you are interested, I can provide a copy of that. It has a whole analysis of the link budget with all these results. And that's part of the effort of this SBIR project that we are pursuing. So let's talk about hardware. We're designing the transceivers. So this is typical, as I said, the OOT has 6 transceivers. So this is one of them. To give an idea of scale, it's 4 inches by 4 inches. This is about 1 U. The depth is a little shorter, but it's 0.7 U. But anyways, 4 inches by 4 inches. You can see the optics. And so we actually build those. We are testing them. You can see here one of them. You can see we're doing testing. Like you can see, we are actuating the steering mirror, and we are pursuing different tests, including pointing acquisition and tracking. So that is ahead. The system is working as expected. Oh, another thing we are doing, which is critical for the OOT, is the angle of arrival. So what is that? The angle of arrival, what it does, it uses an array of detectors. This is an OOT, a smaller version of it. You see these detectors? This has 60 detectors. So what it does, we create a beam, a large beam, using this beam expander. So the beam is about 10 inches in diameter. It illuminates the whole OOT. So the detectors pick different amounts of power based on their positions. And with that, you can actually get very accurately the direction of the incoming beam, and that is azimuth and elevation. So we spent a lot of time on that technique and on that system. So another thing I should mention is there's a rotary table here. So what we do is create a beam, then begin rotating the OOT. So to the OOT, it looks like the beam is moving, obviously, but around the OOT. But in reality, it is moving due to the automated rotating stage. So this is an average on the OT. You have the detectors, 20 detectors. This is the GUI of our OT system, our angle of arrival system. And so what you see here are the values we're measuring from each detector in this array. And in here, the graphic, this seeks to represent the OT. And you can see there's a beam there. So that is a solution. That's the angle of arrival. So as you run this, you can see we get the data. We rotate it, and you can see the beam. So this is the direction of the beam with respect to the OT. So as you rotate the OT, you can see it nicely tracks the beam. So we spend a lot of time on this. So we have multiple ways to calculate the angle of arrival. Also, we are including machine learning algorithms to this. So the idea is to achieve millidegree accuracy. So one of the things we also focused for the past few months is on the bandpass filters. So we use every detector has a bandpass filter, and you need to, because you have a wide field of view, you need to use a large bandpass. So we're looking at 60 nanometers bandpass filters, and with that you get some noise in, but that noise is 20 dB down with respect to the signal we get. The typical signal, 500 kilometers, for instance, is about minus 65 dB watt. The noise provided by, say, the sun or the moon, full moon, say, is 20 dB down. So it's not going to affect our IoT. So we have that, we have calculated it, we have results, and we can make those available. But anyway, so that is very robust. It's a very robust system that should provide angle of arrival solutions with millidegree accuracy. So this is a picture of the whole OT. You can see the apertures, the transceivers, the mirrors, all the optics. Here you can see the filters I was discussing. Behind each filter, this is a bandpass filter, there is a detector that I showed before. And you can see the mounting to mount to the spacecraft. So we already have this completed and assembled. One thing we did, actually, now we want to test it. Obviously, what's next? We want to test this device, so we want to do baby steps. So the first thing we want to do is get the OT. You know it has 6 transceivers. So we're going to get one of those. We put a crown to it, which is the AOA, put a processor, and then becomes a single optical terminal. So it's part of the OT, but it's also a single optical terminal, which we want to commercialize that. And so again, this device, you can see pictures of it here, should provide up to 12 gigabits per second, plus minus 45 degrees steering, if you're interested in that, and 1 watt of power. And the aperture is 50 millimeters. So with that, you can do the calculations. You can use it in your spacecraft if you need. But this will be available in a few months. So we plan to fly this in a few months. We're going to do a balloon flight. And early next year, we're going to do a LEO flight with a partner, and a university partner in Australia. Anyway, so this is coming, and we are going full steam ahead, and we are very happy with the results we're getting so far. So this is the LEO mission we're planning for early next year. And for the ground stations, we're also looking actively, as I indicated before, we're looking at different optical ground stations. We're looking at the low-cost optical terminal that NASA Goddard is developing. There's a Raptor terminal optical aperture, 1 meter aperture that University of Arizona and Arizona State University are working on. So we are also working with them. And also in the Canary Islands in Spain, we are also working with there's an observatory in the Canary Islands. They have a 1 meter optical ground station. And we already signed NDA. We are working on an MOU to use the optical. So we are going in different directions, designing the terminal and also the ground stations. So that is that. So Cornell University is providing the CubeSat for our test early next year. actually, Cornell University is flying, as we speak, I think 3 CubeSats. And they are planning to launch at least a couple of CubeSats every quarter. So we have multiple opportunities to test our various components of the OT. And for the ground terminal, we're also working with PhotonX in Arizona. This is my last slide. And this shows kind of a roadmap. It's getting busier by the minute, but key things, this is step 2 is the balloon flight that we're preparing for in a few months. And then the next one would be the LEO mission, both with Cornell University. Then we hope that to have a flight unit by end of 2025 and fly the system in early 2026 to do a LEO demonstration. We hope that we'll do a Cislunar testing in the 2027, 2028 range. With that, I think I ran out of time. Yes, thanks for your attention, and open to questions if we have time. Otherwise, you can find me in the halls if you have any additional questions. Thank you for your attention. All right.
Thank you, Dr. Velasco. Now I would like to introduce Dr. Naresh Dio from Keenstar Technology, presenting their abstract on advances in technologies for transmitters for CubeSats.
Morning. This is the last day and the last talk of the day. So I am really happy for that because I have been told I have infinite amount of time for this talk. And other good news for me is that this is the last day, last talk. So most of the background for what I'm going to talk about has already been covered. So I can pretty much go as fast as needed on those parts. So first, let me give you a brief introduction and motivation for the need for a new generation of transmitters for small sats and for CubeSats. Then I will discuss some of the prerequisites or critical requirements that are particularly suitable for CubeSats, for the transmitters for CubeSats, and discuss what technologies or what part of electromagnetic spectrum is typically used in the past, at present time, and more importantly, in the future. Then I will discuss some items with respect to the state of the art and go to the most important part of my presentation, which is to discuss the advances that have been made, that are currently undergoing, and some future enhancement to transmitters for small sats and CubeSats, and that is really the crux of this discussion. If time permits, I'll give some of the examples of what we are going to talk about. So, why a new generation of transmitters for CubeSats and small satellites? Because the need for data and the quantity of data is exploding in terms of how many gigabytes or terabytes of data per pass many of the current instruments and satellites are having to generate, and therefore some new technologies or new frequency ranges may be needed. Then, of course, always a great concern is to reduce the swap, which is particularly important for CubeSats. So smaller size, weight, power consumption, and of course the cost. And of course, performance is of very significant importance to us, and that can be in terms of power consumption or reliability or any other criteria that your particular application might have. And finally, it's important to have commercial availability of these. So the people who are generally creating a payload, which may be a science payload or anything else, would not have to worry about developing their own transmitters. And this is true of companies that are launching large number of satellites so that they don't have to deal with proprietary technologies for their transmitters. Now, transmitters are everywhere, whether you are in a communication domain or you have a sensor or a radar, you need transmitters, because without a transmitter, the satellite is just a orbiting piece of junk. So, because it cannot talk to its ground stations or perform its radar or other functions. So, what is important for the transmitters is small size, as we discussed earlier. They have to be lightweight. Again, prime power is always in short supply, so they have to be as efficient as possible in their transmitter power generation. Then today's discussion, I will largely focus in frequency ranges from 8 to above 76 gigahertz. Then the other requirement for CubeSats and other small satellites is scalability of output power of the transmitter. It could be from below 1 watt to 25 or even 50 watts of transmit power, depending on your application, whether you are dealing with a radar or with a communication link or just your data transfer. They should be highly reliable, obviously goes without saying in the space application. Modularity of design is what this conference is all about, conforming to standards and conforming to certain form factors. Affordable, of course, and finally, they should be mass producible, because the number of satellites, especially CubeSat, that are being launched every year is exploding, and therefore one should be able to mass produce. So this talk is largely to encourage business or industry that is in the business of making hardware to consider the next generation of transmitters based on what I'm presenting here today. This is just a quick look at what are the technologies that are currently, or what are the frequency ranges or part of the electromagnetic spectrum that is currently being offered, and then a little bit of the things which are just about to happen. So, of course, optical links are being developed as we speak. Some of them were presented here today. They are particularly good for inter-satellite links, but they may or may not be yet ready for CubeSats to ground, though that has been demonstrated in the very recent past. In the microwave domain, you have the S-band that most of the people who presented their material used, or X-band, and then KKA band, which are slightly higher in frequency and are used by those who generate a vast amount, terabytes of data per day, to download their data. And then I'm going to talk briefly about QV band and E band and W band, which are much higher frequencies, and yet they have some serious advantages here. And of course, the application is for communication, for radars and sensors, for data transfer, and many esoteric applications or uses of transmitters that are coming up now. This is just a very quick look at the frequency bands that are currently being used. And you notice the plot on the chart on the right shows that many of the CubeSats and other small sats have more than one transmitter, more than one frequency they are using simultaneously or for different functions. So, but there are trade-offs associated with going to the next generation of transmitters or data links, as the case may be. They have to conform to the available volume or available space, and also have to respect the prime power that is available and the data rate. You have to select a technology or a frequency range where the data that you are trying to transfer can be supported. The enemy of high frequency is the atmospheric attenuation, because it tends to be much higher, especially in adverse weather, fog, rain, and snow. So one has to take that into account when picking your mission or picking the transmitter for your mission. The antenna, however, is on your side. The antenna size decreases proportionate to the frequency, higher frequency you are using. So you can get a lot of gain or a lot of directivity from your antenna when you go to higher frequencies. So let's quickly jump into the 5 or 6 advances that are taking place currently or have been taking place for the last decade or part of a decade and will continue to take place that will promote the use of transmitters using solid state power devices. So gallium nitride, as opposed to gallium arsenide or CMOS or other technologies that are available for transmitters or for data links today, gallium nitride is perhaps a game changer. Its efficiency in terms of RF power produced for a given amount of DC power, the amount of power it can generate, and can operate at pretty high junction temperatures. So it can operate in a very reliable condition for long periods of time. And the other part is that the bandwidth that you can achieve at higher frequency, especially using gallium nitride, is very conducive to use for high data rate applications or for special applications. Its power is scalable from under 1 watt to more than 50 watts as needed. So the other item that was presented in number of talks before me was regarding the thermal management or the design for thermal. So that's critical for these higher frequencies because the efficiency tends to be lower than at lower frequencies or the next generation. Even though we are talking about gallium nitride being efficient, is nowhere near what S-band or X-band is. So there is a need for better thermal management, and therefore we had learned about oscillating heat pipes, interfacial layers, and use of new materials, and also much more importantly, use of printed circuit boards that have thermal management built into them for higher frequency as opposed to traditional technologies. So all these add to more efficient transmitters and better removal of power, so with less load on the system. Then other part, which is now we are getting into the circuits aspect of it, is availability of surface mountable devices or surface SMDs as they are typically called. And these devices, particularly at higher frequencies, are increasingly being available, and they have direct impact on reducing the size of your transmitter or your data link or what have we here. And more functionalities are being crammed into these ICs or into these surface mountable devices. So it has the impact of further reducing the surface area of your circuit board. So they can easily conform to a CubeSat format. And the other part is that we are now dealing with active electronically scannable arrays of antennas that allow you to steer the beam and also are very amenable to using surface mountable devices that are distributed as opposed to a single source of transmitter power. So this is a whole new generation of transmitter antenna combinations that we are beginning to see and that we will continue to see. Additive manufacturing, or 3D printing as it is often called, is another important part of this new generation of transmitters, because many of the structural part as well as circuit parts can now be implemented, particularly at higher frequencies where we are able to make filters and waveguides and other structures which serve as part of the transmitter. And of course, the nice thing about additive manufacturing or 3D printing is that it results in reduced mass and often reduced size because there are no screws or other hardware items. So the mass is lower and size can often be much smaller. And we can print crazy things with this technology, which are particularly of interest in high frequency. Combining many of these functions using 3D printing or additive manufacturing really is going to be very helpful in this next generation of transmitters. And use of commercial off-the-shelf electrical, electronic, and electromagnetic components is another important part of these new transmitters. We cannot continue to use application-specific parts or proprietary parts for this generation of parts. So availability of CART's part has certainly increased or improved over the last few years, and that will contribute to much better, lower cost, lower swap transmitters or links, data links in the of the future. Now, I didn't talk about software-defined radios yet, but software-defined radios using this new technology will be yet another added asset to the people using transmitters and being able to change the frequencies or transmission modes at their will. Of course, this conference is all about modularity and standardization, and that certainly is an aspect that will be heavily used in creating this generation. My talk is largely about encouraging the industry and manufacturers of parts for CubeSats and for small sats to seriously consider. So it's a missionary statement more than just an academic thought at this point, to encourage industry to start thinking of commercially off-the-shelf transmitters at these higher frequencies or with higher capability than in the past for those users who really need that. And finally, the new space qualification methodology or philosophy and testing is going to be very significant, because these are new technologies, so to get them qualified and tested so the users can, with impunity and with comfort, use these transmitters without having to either develop them using proprietary technology or without having to be concerned about qualifying them yet another time. I have some breaking news, which is from this morning, that one of the technologies I talked about was E-band or W-band or QV band. So just yesterday, SpaceX announced a contract with an English company to produce the transmitters that I'm just talking about today for their latest generation of Starlink and other large data handling constellation of satellites. So this is just, they have been playing with it for a long time. So the QV band, and generally the purpose of that is to transport data to the ground stations rather than to the user, where they need as big a pipe as they can use. And for CubeSats, it's certainly possible, not only possible, it has been done to use these high frequencies. There are at least 2 CubeSats that have been going over Europe for last 2 to 3 years now that use 76 gigahertz, which is in the middle of the high band, and have successfully been transmitting data over Europe and doing propagation studies of characteristic of atmosphere over Europe, which tends to be pretty nasty for last few years. So these are just not hypothetical thoughts. The future is here as far as this is concerned. And I think that's about most of the things I wanted to talk about, but I would encourage you to ask questions after this presentation, which is the last one, and many of you are trying to rush to your cars, but I will be happy to answer any questions after this. Thank you. And now time for any questions. Oh, people are spellbound. So I had decided that if nobody asks me any questions, I will ask a question myself and then answer it. So my question is, how long before these transmitters become commercially available? I do not have a clear answer, because most of the companies that have developed these transmitters presently are either for their own use in higher frequencies, that means frequencies above 25 gigahertz, or even frequencies above 18 gigahertz are for their own use, so they're using proprietary technologies, and or there are companies which are dedicated to a single customer. For example, Filtronic, the company in the UK, is working with SpaceX. However, I would very much hope that the community that's in the business of making transmitters and other components for CubeSats will pay attention and start producing low cost, low swap transmitters or data links. You have a question there? So I'm sorry, I didn't quite get your question.
Yeah, so the traffic is another issue. So when you select them,
Well, maybe I can answer the question in a way. The issue of, are you talking about inter-satellite links or just satellite to ground links? Satellite to ground, again, is a matter of how many ground stations you have, how many, and the diversity issue, because very often if you have multiple ground stations and one of them is in inclement weather, then you can use another ground station and get the data out, because weather is one of the issues. But typically, because these satellites have, these transmitters will have relatively narrow beam, it can still communicate with most of the stations pretty well. I hope that's answer to your question. Anyone else? Well, since this is the last talk of this wonderful conference, let's give it up for all those who presented there. And let's give it up for all the volunteers here who helped this conference become a great success. Thank you.
Hello, everybody. Thank you so much for coming to our 2024 CubeSat Developers Workshop. This is our 21st annual workshop here at Cal Poly, and while we started it here 21 years ago, it wouldn't be possible to have it going as long as it is without all of you. Your support, whether you're attending, you've got a booth outside, you presented, whatever way you showed up this week, it means so much to us, and we as a lab have learned so much from all of you as a result. I know I am leaving this week so inspired, and I've got a massive list of things I'm ready to Google and keep learning, so I am so ready for next year. I know right now I'm supposed to talk about some amazing moment or one memory that really stuck out, but I can't come up with one. It's been such an incredible week, and I've had so many amazing conversations with so many people that there's not one that stands out. Every single person here had something incredible to share this week, and I feel so lucky to have met as many of you as I did. Whether you're a returning member to workshop or this is your first year here, we're so glad you are here, and we hope you can join us next year. Now, I know this next part's going to feel a little counterintuitive because you've been sitting here listening to presentations, but I want everybody to take out your phone. I know you haven't touched it much these last few days, but pull it out right now, open up your calendar. Whether you use Google Calendar, Apple, something else, pull it up and pull up April 2025. I know, we're going a year out here, kind of crazy, but take April 22nd through 24th and mark yourself unavailable. Because all of you, you're going to be right here, right, next year? Yes, that's what I'm talking about. April 22nd through 24th, 2025 is CubeSat Developers Workshop, our 22nd one. And also, don't forget to think about submitting abstracts for next year. Our website, our email list will have all that information, but start thinking now about what you want to talk about because we can't wait to hear from all of you. Finally, we have our career fair beginning right now in the PAC Pavilion that is downstairs where the F Prime workshop was held this year. If you don't know where that is, follow somebody who looks like they know where they're going, probably somebody in a green polo, but we'll all be downstairs. Career fair starts right now if you signed up for that. And have a great rest of your week, safe travels home, and we hope to see you next year. Thank you so much.